So next topic is 3 CNF satisfiability. So we have discussed what are 3 CNF and what is meant by 3 CNF satisfiability. Anyway, let's have a quick look at this 3 CNF. So we can define this 3 CNF satisfiability using the following terms. Okay. So a literal in a Boolean formula is an occurrence of a variable or its negation. That is a literal. Then a Boolean formula is in conjunctive normal form or in CNF if it is expressed as an AND of clauses, each of which is the OR of one or more literals. A clause means it is one or of one or more literals, and CNF means it is a conjunction of disjuncts or AND of clauses. Okay, a Boolean formula is in 3 CNF or 3 conjunctive normal form if each clause has exactly 3 distinct literals. Okay, for example, the Boolean formula x1 or negation x1 or negation x2 and x3 or x2 or x4 and negation x1 or negation x3 or negation x4. This is in 3 CNF. The first of its 3 clauses is x1 negation or negation x1 or negation x2, which contains 3 literals x1, negation x1 and negation x2. It should have 3 distinct literals. Okay. So in 3 CNF we are asked whether a given Boolean formula phi is in 3 CNF is satisfiable. Okay, that is the 3 CNF set. And we have a theorem here, and satisfiability of Boolean formula in 3 CNF is NP complete. And with this we can determine that satisfiability of Boolean formulas is unlikely to exist. Okay, that is a polynomial time algorithm for this one is not there, or it is unavailable. Polynomial time algorithm for or to determine the satisfiability of Boolean formula. Okay, so the theorem says satisfiability of Boolean formulas in 3 CNF is NP complete. And again we have two things to prove. First is SAT is element of NP, that applies equally well here to show that 3 CNF SAT is also in NP. We need only show that SAT polynomial time reducible to 3 CNF SAT. Okay, so because SAT is element of NP, which means 3 CNF SAT is obviously element of NP, because if a Boolean formula is in NP, then 3 CNF SAT is also in NP. Okay, where this is again a Boolean formula but with some restrictions. And the second thing to be showed is SAT as polynomial time reducible to 3 CNF SAT. So we are reducing from SAT, that is a Boolean formula, we are converting it into a 3 CNF SAT, or reducing this Boolean formula into a 3 CNF SAT, and that is done in polynomial time. And this reduction algorithm can be broken into 3 basic steps. Okay, and each step progressively transforms the input formula phi closer to the desired 3 conjunctive normal form. So the reduction is from a Boolean formula, that is from SAT to a 3 CNF SAT, and that can be done in 3 basic steps. And what happens in each step is that each step transforms the input formula. This is your input formula phi, that is transformed into closer to desired 3 CNF form. Okay, so the first step, okay, that is similar to what we do for circuit SAT reducible to SAT. So the first thing is we are trying to construct a binary pass tree for the input formula phi with literals as leaves and connectives as internal nodes. Okay, so the Boolean formula. So our aim is reducing from SAT to 3 CNF SAT. So we have a Boolean formula with us that we can call it as phi, and we can construct a binary parse tree with this phi. So in this binary parse tree, the literals will be the leaves and connectives will be the internal nodes. Okay, this one will is actually a representation for this Boolean formula, that is x1 implies x2, etc. Okay, so x1 x2, so it says x1 implies x2, so x1 implies x2. Then here it says negation x1 if and only if x3. Okay, so negation x1, this is x3, that is connected by this if and only if. Okay, then this one is connected with x4 using logical OR, so that is here. Then the whole thing is negated, so this result is negated, and we have these two, there is a parenthesis for this, and these two are connected with a logical OR, so that is connected with a logical OR. Then this one is there is a parenthesis here, so the parenthesis ends here, so that this is connected with a negation x2 using this AND. Okay, this is the parse tree corresponding to this Boolean formula. Okay, so should the input formula contain a clause such as the OR of several literals, associativity can be used to parenthesize the expression fully, so that every internal node in the resulting tree has one or two children. Okay, so even if the clause has clause means that is OR of several literals, we can use the parenthesis, and the resulting tree will have, each node will have one or two children. The binary parse tree can now be viewed as a circuit for computing the function. Okay, so this binary tree we can view as a circuit for computing the function. So that's what happened in the case of a circuit set. So we have reduced this circuit set to SAT. So here we are reducing from SAT to 3 SAT, 3 CNF SAT, and here corresponding to this SAT or a Boolean formula, we are constructing a binary tree, and we can consider it as the circuit for computing the function. So introduce a variable yi for the output of each internal node. Okay, so we can use a variable yi for each output of the internal node. Okay, output of each internal node. Then we can rewrite the original formula phi as the AND of the root variable and a conjunction of clauses describing the operation of each node. So we can describe this phi, that is the original formula, as the AND of this root variable, okay, then and a conjunction of clauses describing the operation of each node. Okay, so here, so we can write this Boolean formula as phi dash. Okay, so phi dash is equal to y1 and, okay, y1 and y1 is if and only if y2 and negation x2. Okay, so in the parse tree we can see that this formula is y1, and we know that this is actually, we can write the Boolean formula using the root variable, then AND with what, conjunction of clauses describing operation of each node. So y1, operation of the first node is y1, that implies, okay, y2, then AND negation x2. Okay, so how can you write it? Sorry, how can you write it? So here this y1 formula will be like y1 and something. Okay, so this y1 and what does this y1 mean? Y1 if and only if y2 and negation x2. Okay, and we can write y2. Y2 is if and only if. What is y2? That is y3 or y4. Okay, then what is y3? Y3 is y3 if and only if x1 implies x2. Okay, then y4, what is y4? That is negation, that y5. Then what is y5? That is that implies y6 or x4. Okay, then what is y6? That is negation x1 if and only if x3. Okay, so like this you can write this expression, this formula. Okay, so this is known as phi dash. So your input is phi. From that you have constructed a path tree, and based on the path tree you can write this Boolean formula. You can call it as phi dash. Okay, and this is written like this. It is actually AND of the root variable and a conjunction of clauses describing operation of each clause. It describes operation of each clause, operation of each node. Okay, so this tree or corresponding to this phi is rewritten as phi dash, and observe that the formula phi dash thus obtained is a conjunction of clauses. Okay, clauses phi I dash. You can call each of these clauses as phi I dash, and each of this has at most 3 literals. Some of them has 3 literals, not all. So that's why each of which has at most 3 literals. So you can consider all this as clauses. Okay, so the entire formula phi dash is actually obtained is actually a conjunction of clauses, and each of these clauses you can call as phi I dash. Okay, and each of this phi I dash has at most 3 literals. Then the only additional requirement is that each clause be or of literals. So you got AND of clauses. Okay, and your second condition is that each clause should be or of literals, and then each clause must have 3 distinct literals. Okay, so the first condition is there, it is AND of these clauses. Okay, that is available now. Then second step after reduction converts each clause phi I dash into normal form. Okay, so our aim is to convert this into each clause phi I. So it should be or of literals. Okay, so we constructed two. So what we can do is that for converting this each clause phi I dash into CNF, we constructed truth table for phi I dash. That is, for each clause we can construct a truth table by evaluating all possible assignments to its variables. Okay, so you can evaluate all possible assignments, and suppose, and we know that each clause will have maximum 3 literals, so the truth table will have maximum 2 power 3 entries. Okay, so which means 8 entries will be there for each clause in the truth table, which means there will be only 2 power 3 rows in the truth table. So each row of the truth table consists of a possible assignment of the variables of the clause together with the value of the clause under that assignment. Okay, so you can consider each of this each row of this truth table that consists of a possible assignment of the variables of the clause together with value of the, okay, so that assignment and value of that assignment, okay, or value of that clause under that assignment using the truth table entries that evaluates to 0. Okay, so what we are trying to do is that we take the truth table entries which evaluates to true, and we build a disjunctive normal form, that is DNF, or it is an OR of ANS, that is equivalent to negation phi a dash. Okay, so which means we are constructing negation phi a dash. It is an OR of ANS. We then convert this formula into CNF formula phi a dash by using De Morgan's laws to complement all literals and change ORs into and ANS into ORs. Okay, so what we are trying to do is that we'll take each clause phi a dash and we construct a truth table for that, and we'll take the truth table entries that evaluates to 0. Okay, and each row in the truth table will actually contain assignment of the variables of the clause and the value of the clause under that assignment. Okay, these are the entries in the truth table, and we'll take all the truth table entries that evaluates to 0. Then we build a formula in disjunctive normal form, that is DNF, that is actually an OR of ANS. Okay, OR of ANS. Then we then convert, so we'll get an OR of ANS, then we'll apply this. What we need is CNF. We get a DNF, what we need is a CNF, which means it should be an AND of ORs. So for that we apply De Morgan's law. When we apply De Morgan's law, we know that all the ORs will be converted into AND will be converted into OR. Okay, so we can apply this thing. So next step is the truth table for one. Let us take one example for this clause phi 1 dash, that is y1 if and only if y2 and negation x2 into CNF. So we are trying to convert this into CNF. So the truth table for phi 1 dash is given below. Sorry, the truth table for phi 1 dash is given below. That is, we have y1, y2 and x2, 3 literals, and these are the values for the variables in the clause, and this is value of the clause under this assignment. What is value of this clause under assignment? Okay, so we have there are 3 literals, so there will be 8 entries in this in this truth table, and 1 1 1. So you can substitute for y2 and negation x2 and y1. So if this is true, then you can give 1, otherwise 0. So for this case it is y2 and negation x2. Okay, so this will evaluate to 0. So 1 if and only if 0, so which means that is false, so 0. So like that you will get all these values. Okay, now so corresponding to the assignments you get either 0 or 1. Okay, so the this formula will be evaluated to either 0 or 1. So next step is you will take all the entries which evaluates to 0, that is this one and this. So 4 entries are there which evaluates to 0. So you will take each of them and you can write it in DNF. Okay, that is OR of ANS. That is that you can call as negation phi 1 dash, and that is this y1 and y2 and x2. Okay, or y1 and negation y2 and x2. Okay, this then or y1 negation y2 and negation x2 is, or negation y1 and y2 and negation x2. So you get a DNF formula like this. Okay, So you get this negation phi 1 dash. Then you can apply De Morgan's laws, okay, and we get the CNF. So when you apply De Morgan's laws, all the ands will be changed to or, and or will be converted to and. So you can call that formula as phi 1 double dash. So your original formula was phi 1 dash. So you have phi, then you have constructed phi dash, then from that you take phi 1 dash, one clause, and now you are converting that into phi 1 double dash after applying De Morgan's laws. So you get negation y1 or negation y2 or negation x2 and, okay, so just convert this into De Morgan's law, apply De Morgan's law and convert this. So you will get formula like this, and negation y1 or y2 or etc., and which is equivalent to the original clause phi 1 dash. Okay, both will be, this two will be the same, phi 1 dash and this one will evaluate to the same thing, and each clause phi I dash of the formula phi dash has now been converted into CNF formula phi I double dash, okay, and thus phi dash is equivalent to the CNF formula phi double dash consisting of the conjunction of the phi I double dash. Moreover, each clause of phi double dash has at most 3 literals, okay. So now we get for each clause, so for one clause we have constructed like this, okay, and you can repeat this for each of the clauses, okay, and you can combine them. So this one is actually in CNF form. So when you convert everything into this form, you will get a CNF, okay. Then each of this clause in phi double dash has at most 3 literals, not exactly 3 literals, it will have at most 3 literals, okay. So the third and final step of the reduction further transforms the formula so that each clause has exactly 3 distinct literals, okay, that is our aim. So you got this kind of CNF now, and here each clause has at most 3 literals. Now we are trying to convert this into a clause which has, or each clause will have exactly 3 distinct literals, okay. The final 3 CNF formula phi triple dash, okay, this is actually triple dash. Phi triple dash is constructed from the clauses of the CNF formula phi double dash, okay. So the final 3 CNF formula you can call as phi triple dash, and that is constructed phi double dash, and it also uses 2 auxiliary ways that we shall call P and Q. So for constructing this, so in some cases, so what is the problem with the formula we constructed so far? So that contains at most 3 literals, not exactly 3 distinct literals. So if it has less than 3 literals, then anyway we need to make it to a 3 CNF form, in 3 CNF form, which means each clause should have exactly 3 distinct literals. For that, we anyway each clause will have at least 1 literal. So what we are doing is that we'll take 2 auxiliary variables P and Q. Each clause CI of phi dash, we include the following clauses. Okay, if CI has 3 distinct literals, then simply include CI as a clause of phi triple dash, okay, which means if CI has 3 distinct literals, then there is no question, it is in CNF, so we can simply include that in phi triple dash, okay. If CA has 2 distinct literals, okay, that is CA is L1 or L2, where L1 and L2 are literals, then we can include one new auxiliary variable, that is P, and we can rewrite it as L1 or L2 or P and L1 or L2 or negation P as clauses of phi double dash, okay. The else P and negation P merely fill the syntactic requirement that there be exactly 3 distinct literals per clause. So it doesn't have much meaning, but it is just for fulfilling the syntactic requirement, that is each clause should have exactly 3 distinct literals. Okay, so we are including P and negation P, and when we are including P and negation P here, it is equivalent to L1 or L2, whether P is equal to 0 or P is equal to 1. It is irrespective of this term, we will get L1 or L2. Okay, and third condition is if CA has just one distinct literal. So what happened here, if CA has two distinct literals, then we will get each clause. Okay, each clause with two distinct literals will be converted into two clauses. Okay, we get two clauses here. And suppose this clause CA has just one distinct literal, then we should include two auxiliary variables P and Q, and you should write 4 clauses corresponding to this literal L, that is L or P or Q, and L or P or negation Q, and L or negation P or Q, and L or negation P or negation Q as clauses of phi triple dash. Note that every setting of P and Q causes the conjunction of these 4 clauses to evaluate to L. Okay, so we should have these 4 literals, and every setting of P and Q causes conjunction of these 4 clauses to evaluate to I. Whatever may be the assignments to P and Q, this will finally evaluate to I. Okay. And we can see that the 3 CNF formula phi triple dash is phi triple dash. Okay, phi triple dash is satisfiable if and only if phi is satisfiable by inspecting each of the 3 steps. Okay, like the reduction from circuit sat to sat, the construction of phi dash from phi, the first step preserves satisfiability. The second step produces a CNF formula phi double dash that is algebraically equivalent to phi dash. And the third step, that a 3 CNF formula is produced, that is known as phi triple dash, that is effectively equivalent to phi double dash, since any assignments to the variables P and Q produces a formula that is algebraically equivalent to phi double dash. Okay, so whatever we do, all these 3 are equivalent, and that preserves, if they are equivalent, then it preserves satisfiability. Okay, and this is the reduction. Okay, so for reducing from a SAT to 3 CNF SAT, so we have a SAT that is a Boolean formula, then we are constructing that into binary tree, and we write the Boolean formula from the binary tree. We can call it as phi dash. Then we take each clause. Okay, we take each clause in that, and we are converting for each corresponding to each clause, we construct a truth table, and from the truth table we take truth assignments corresponding to the 0 output, and we convert that into a formula, and we can call it as a DNF, that is OR of ANDs. We get OR of ANDs corresponding to this 0 values. Then you apply De Morgan's law, by which you get an AND of ORs or a CNF. Okay, and the corresponding CNF, okay, that will have at most 3 literals. If it has 3 literals, then you can output it. Otherwise, if it has just 2 literals, then you will introduce one auxiliary variable, and you will have 2 clauses corresponding to a single clause with the 2 literals. And if the clause has just one literal, then you add 2 distinct literals or 2 auxiliary literals, and you will have 4 clauses corresponding to a single literal. Okay, likewise you get a 3 CNF. and we are saying that it protects the satisfiability or it preserves the satisfiability, because each of these three steps are equivalent actually. Okay, so that preserves the satisfiability. Okay, so you can verify all these things. This will be same as the original clause, and you can verify that. Okay, so when you take this zeros only, this will be satisfiable for the truth values. Okay, so if it is 1, then corresponding to that, if you give the same truth assignment, this will evaluate to 1. Okay, so you can verify that, you can do as homework. Then what we are trying to prove is that this all these steps should be done in polynomial time. Okay, the reduction can be computed in polynomial time. So constructing phi dash from phi, okay, introduces at most one and one clause per connective in phi. Okay, then constructing phi double dash from phi dash can introduce at most 8 clauses into phi for each clause from phi, since each clause of phi has at most 3 variables and the truth table for each clause has at most 2 power 3, sorry, this is 2 power 3, that is equal to 8 rows. The construction of phi triple dash from phi double dash introduces at most 4 clauses. Okay, at most 4 clauses, because if there is a single literal, then you will have 4 clauses. If it has 2 literals, you will have 2 clauses, etc. Okay, so at most 4 clauses will be there. Thus, the size of the resulting formula is polynomial in length of the original formula. Then each of the constructions can easily be accomplished in polynomial time. Okay, so that is the proof that this 3 CNF is NP complete. So you have proved that 3 CNF is in NP because CNF is SAT is in NP. Then you are reducing SAT to 3 CNF, and you are saying that each of this will take only polynomial time, because only fixed number of clauses will come, so that can be done in polynomial time. Okay, that's it.